These are the notes that go with Chapter 16 in the McGraw-Hill chemistry book. It's the first day, Notes A. So Chapter 16 talks about reaction rates. Much like our car has a speed, reactions have speeds. And we don't use speedometers like we do in our car, but we use some other tools in order to determine the reaction rate. One of them might just be a stopwatch. There are reasons why reactions go fast or slow, and we're going to find out all that stuff today. First of all, reaction rate. What is it? Reaction rate is the speed of reactants turning into products. Now, we're going to deal with this speed based on the reactant side. You might say, well, how do we know how many products there are? Think about an hourglass. You turn over an hourglass, and it starts trickling sand out. Let's say it's losing 10 grains a second of sand. If you know that it's losing 10 grains of sand from the top, do we know how fast the sand is accumulating on the bottom? Well, sure we do. It's the same rate. So if we know one, we know the other. And it's the same thing with reactions. If we know how fast the reactants are changing, then they're changing in the products, so we know how fast products are changing. So we write our reaction rate based upon the change in reactants per second. And when we say change of reactants, it's the concentration of reactants, which we're usually going to deal with in molarity. If you remember, molarity is moles per liter. One of the questions on your review asks, what are 2 units of reaction rate? Well, molarity per second or moles per liter per second. That will be moles with liter and second on the bottom. And sometimes those are designated like mole, L to the minus 1, S to the minus 1. The minus 1 means it's on bottom. So the minus means it's in the denominator. So we're going to talk about collision theory a little bit. It just is a logical way that we use to explain how reactions go fast or slow. Collision theory says that molecules have to collide in order to react. And they have to collide with enough force to react. So the more collisions, the more reactions. And then you have to think of, well, how do we speed up collisions? Well, if you have one student out in the hall, chances are he's not going to collide with anybody unless he's got an invisible friend. But if there are 100 kids out there, especially between bell passing periods, also maybe on a fire drill, then there's going to be some collisions, okay? The more students, the more collisions. Same thing with molecules. Higher concentration, more molecules, more collisions. We could also heat them. Temperature. We increase the temperature, they speed up. Not only are they going to collide more often, but they're going to collide with more force that's going to make the reactions occur every time. So we'll talk about more of those. How do we speed up collisions? But understand, when we talk about collision theory, it is the fact that the collisions have to happen for reactions to occur. When reactions occur, the reactants, they'll collide or do whatever they do to start reacting, and we have what we call an activated complex or transition state. That is the kind of the morph of products and reactants. It's not a reactant, not a product, it's in between. They're kind of doing the dance in order to become a product. And we always find this activated complex at the top of the energy hump that we call the activation energy. So one of the things you're going to be doing in this chapter is you're going to be drawing some energy diagrams. And whenever you're asked to do that, first thing you need to do is to draw an L shape, which is your graph basically. 0 in the bottom corner. This is energy. We'll just use an E for energy. And this is time. So as time passes, arrow to the right, so does the reactant. So we're going to talk about some complex reactions that have more than one hump. We're also going to start out with just a simple reaction that has one hump, and that would be where we have reactants, R for reactants, P for products. Here's our activation energy, okay? So I'm going to just label it AE, activation energy. Here's our activated complex or transition state. It can be called either one, so either name works. And So I know these are tough to see on the board, but you've got the notes next to you and you could look at those. You should be able to draw one of these diagrams and label it. And there's always a title on every graph and every diagram, so we're just going to call it title there, but it'll be something appropriate for the reaction you're doing. So maybe the reaction of hydrogen and oxygen combustion. So that's most of the parts. Now notice that the reactants are above the products. This is our delta G, which tells us our Gibbs free energy. If it's a spontaneous reaction here, then obviously the products, this is how you do this. You put a dot on the reactants and go to the products. If it's a downhill slope or a negative slope downhill, then it is spontaneous. If it is an uphill reactants to products, then it's not spontaneous. Yes, I understand there's activation energy in front of it, but that's kind of like pushing a car. You got a little bit of a speed bump and you got a gas station down at the bottom of the hill, so your friend hops in and you just push it over the speed bump, and don't try to jump in. That's too dangerous, but you'll just meet them down, push them down, and they guide it down to the gas station. It goes on its own. But if the gas station were up on a hill, not so easy. You're going to have to be pushing it up the hill, which may not happen. That would be like a non-spontaneous, not happening on its own. Yes, you still have to push it. Lighting dynamite, so spontaneous reaction. But once you do the activation energy, which is lighting the fuse, then run, go somewhere else. But the idea is that it's going to go off. Okay, so this is a spontaneous reaction because the reactants are higher than the products. So I've covered all of that, and we'll move on. Here's some different pictures of energy diagrams. Hopefully you have these notes in front of you. If not, they're available online, PowerPoint A. Notice that I've got transition state instead of activated complex. Notice that the last one has two humps. This is what we call a complex reaction, and that's one of the answers in your review, a reaction, not action, but a complex reaction. It's made up of two or more elementary reactions or subreactions. And something you need to know about those, I will be asking you to look at a graph and analyze it. So I'd ask you to look at this third one and say, how many subreactions are there? Well, there's two humps, so there's two subreactions. Every subreaction has a hump, so you can count those. The first one has a long uphill climb, so it is the slow reaction. The second one, not so much. That's how you determine whether it is a slow reaction or a fast one. And the slow reaction is kind of the one that determines the rate, because think about this. Let's say you're eating grapes and eggs for breakfast. Well, the eggs, you're not going to eat them raw. The grapes you can. So the eggs are the slow part of breakfast and the grapes are the quick part. How long it takes you to make the eggs is what determines how long it takes you to eat the breakfast, right? That's a question on your review. The part of the reaction of a complex reaction that affects the rate the most is the slow step, because it takes us a while to cook the eggs. I mean, we could grab the grapes and take off right away. When we get through cooking the eggs, we grab the grapes and we go eat the eggs and grapes, which is kind of an odd breakfast combination, but it works for this example. So you get the idea there that the slow reaction is the one that more determines the rate than the fast one. Look at the height and look at the number of humps. This tells you some things about a complex reaction, and we'll talk about those later. Spontaneity and reaction rate, like we said, a positive gives energy where we start low and go high. That is positive, will not be spontaneous. Start high and go low will be spontaneous. Easiest way to do that, especially if you have lots of humps in the reaction, is to put your finger on the reactant and then go to the product. If you're going downhill, negative slope, spontaneous. So these are the 6 things that that affect reaction rate. And I don't want you just to know the 6. I want you to know how they affect reaction rate. Because the way I ask this in the quiz and the test is name 6 ways you would speed up a reaction. So now I need to know a little more, not just things that affect it. First of all, you'd pick things that will react, because if I picked glass and water and threw them in a bucket, you wouldn't expect that to do anything. So that's not going to react faster. So pick things that react quickly. That would make them react faster. If you pick glass and water, not a good choice. Concentration, like we said in the hall, you got one person, not going to bump into anybody. You got 100, there are going to be collisions. The more particles you have, the more collisions. So for a liquid, you would say its molarity would be higher. Higher molarity, higher concentration. For solids, you just dump more of it in. Okay? Larger surface area, smaller particle size. These go hand in hand. They are the same thing. So let's think of a sugar cube. You got a sugar cube, it can only react on the surface. The other chemical or the water or whatever you're reacting with can't get into the inside. If we mash that into little powder, now we got powdered sugar, then it reacts very fast because the other chemical, whatever you're mixing with, can get all around each little granule. Whereas before, the inside granules were locked up, nothing could get to them. We've shown this in a demo in class with the whoosh bottle. Okay, we lit the alcohol, ho-hum, didn't really burn very fast because there was alcohol on the bottom that couldn't burn because it wasn't exposed to oxygen. But when we shake that into the whoosh bottle and shake it up, now it all turns into vapor, and every alcohol has an oxygen next to it. And when we light it, whoosh, it burns. It all burns in a second, as opposed to a long time. So it doesn't have to wait in line. It's kind of like waiting in line at the cafeteria. Okay, here you get your meal and you go. Everybody, all at one time, instantaneous. But remember, large surface area and small particle size mean the same thing. So you can't say both of those for two different reasons. Temperature. You increase the temperature, molecules move faster because temperature is a measure of kinetic energy. Kinetic energy is moving energy. Catalyst. A catalyst speeds up reactions. You used the catalyst in our types of reactions chapter where you had the square test tube, you put in some hydrogen peroxide, you scooped in a little manganese dioxide, and then you got the glowing wood splint. When you put it in, oxygen made it relight. When you took it out, it might have gone out. But when we put it in again, it relights and gets brighter because it's producing oxygen. It produces oxygen even without the catalyst. You could leave it out, and in 2 days, it would do what the catalyst made it do in 2 minutes. So a catalyst speeds reactions up. That's its job. How does it do that? We'll find out in the next screen that it lowers the energy hump. Kind of like running around the track, running around the track with a bunch of hurdles out there. You got higher things to jump over, it's going to take you longer. We lower those hurdles, you go faster. That's what a catalyst does. And then finally, inhibitors. Inhibitors generally lock up a catalyst, but they could cause the reaction to stop because they lock up with the molecules and don't let them react. One way or another, inhibitors slow reactions, much like catalysts speed up reactions. And it makes the activation energy hump taller, so it needs more energy to react. Catalysts kind of like the gas, and inhibitors kind of like the brake on your car. So those are the 6 ways. Know not only the 6, but know whether they speed up or slow down. Here's how catalysts work. On this screen, you can see that the red line is uncatalyzed and the blue is catalyzed. It is a lower energy hump, so the reaction goes quicker because they don't have to climb over that big hill. There's 2 types of catalysts. Homogeneous catalysts are the same physical state as the reactants. Heterogeneous or different state. When you all did the catalyzing of the hydrogen peroxide, you put a solid into a liquid, which is the heterogeneous catalyst. So that finishes up the notes for this first section. Anywhere along the way, if you missed something, you can go back, or if you need to replay it again, get some popcorn, sit down, relax, get comfortable. Try to work some of the review. You could probably do about maybe almost a third of the review from what we went over. There are also some practice pages out there, and work on all that, and good luck.